Welcome to Group 2's presentation summary covering the research paper Blockchain-Enabled Fish Provenance and Quality Tracking System. Our group members are Juan Carlos, Dana, Daniel, and Jose. Now, starting with the introduction of the paper, it covers transparency and how it is a major challenge in the seafood industry. There is a lack of information on fish origin, quality, and temperature records. This lack of information limits innovation and growth in the industry itself. A solution to improve regulatory bodies, buyers, and consumers' confidence is through the incorporation of blockchain technology. Blockchain in the industry. Current blockchain projects are not sufficient in achieving the transparency goal, such as real-time provenance and traceability information is not precise, or these platforms only provide static images of seafood and minimal information on the animal. By incorporating IoT, Internet of Things, and AI, artificial intelligence, alongside the blockchain technology, the team can achieve the aforementioned goals, such as incorporation of sensors allows for real-time data to be deployed over the blockchain, and AI can use machine learning to detect fish quality based on appearance and validate it over the blockchain. Privacy is a concern whenever blockchain is applied in something. To mitigate this, only authorized users will have access to the blockchain. The attribute-based encryption, or ABE, protects and secures the access control to the IoT chain by utilizing decentralized, trusted authorities, such as the ciphertext is decrypted when the attributes provided by the user match the attributes requested. Below is a diagram of how the process actually works. Embedded systems can provide significant data that can determine fish quality, such as odor, temporal, spatial, temperature, and other environmental domains. Using narrowband IoT, these devices can connect to the internet using existing cellular connections, which are very beneficial for the industry since it has not been adapted on a grand scale just as yet. Artificial intelligence can determine fish freshness by using image processing on their eyes, gills, and skin tissue. And below is a photo of an actual image processing taking place. Key contributors for this paper were 1. The proposal of a multi-layer blockchain system for trusted and secure data sharing where an IoT chain ensures data integrity and an ABE chain provides fine-grained access control to the IoT chain with decentralized trust authorities. 2. Develop new IoT and AI technologies for crucial data, which includes mobile app, NB IoT device, electric nose, and image processing, all for fish origin proof, real-time quality tracking, and objective quality assessment. 3. Design and implement blockchain-enabled fish provenance and quality tracking, where the Sydney Fish Market trading platform using real-time data. And 4th, trials and testing of the system with the local fish supply chain, Sydney Fish Market. This research paper is organized with the following topics. First, the introduction. Second, industrial background. Third, related works. Fourth, blockchain-enabled fish provenance and quality tracking system design. Fifth, multi-layer blockchain system with attribute-based encryption. Sixth, implementation and analysis. And seventh, the conclusion. The Sydney Fish Market is a major component of the seafood industry in Australia. It controls over $150 million worth of seafood sales annually. The SFM's fishing supply chain consists of first, fishing near the coast, and then the harvested fish are placed into boxes, which are rented from SFM at local co-ops. The fishers then print labels containing fishing date, the fish species, size, and other relevant information for the fish. And they attach these labels to the boxes. And then the boxes are temporarily chilled and stored in cool rooms and then transported. Once they're transported, then the final step is them being sold, mainly in the form of a Dutch auction. The Sydney Fish Market has adopted the Quality Index, the QI, to guide the measurement of changes in chilled seafood. This guide allows them to check the appearance, texture, and the odor of the harvested fish. Participants in the supply chain, such as fishers, Sydney Fish Market, buyers, consumers, accounting firms, and government departments, all have various demands, such as wanting trusted supply chain data, quality, and the reduction of expenses it would cost to achieve these demands. The blockchain-enabled fish provenance and quality tracking system is designed to achieve, first, real-time fish quality tracking, which tracks the fish temperature and location from catch to sale. Second, objective and reliable fish quality measurement, which measures fish quality from multiple data sources in an objective and reliable way. Third, trusted platform, which provide trusted provenance proof and quality tracking data to all participants. And fourth, fine-grained access control, preserve the privacy of all participants and enable confidential data sharing. Work that has been done that's related to this research paper is FishNet. And FishNet is a demo project showing the concept of combining sawtooth blockchain and IoT for the provenance of fish from catch to plate. Also, a similar blockchain IoT supply chain solution has been commercialized by IBM Food Trust, which provides transparent digital data supply chain service based on the Hyperledger Fabric. Hyperledger Fabric is a private data scheme. It is possible to introduce access control to public blockchains using the envelope encryption, where the data to be saved in public blockchains are firstly encrypted with data encryption keys. The DEKs can be managed in an efficient and fine-grained way using the ABE encryption scheme. AI technology has been widely adapted for fish quality measurement by analyzing the odor and vision data.
The blockchain-enabled fish provenance and quality tracking system is designed to ensure transparency and accuracy throughout the seafood industry. It consists of the following: a blockchain technology, which is used as the trust center, Internet of Things and sensor networks, which are used to retrieve data from the environment and the fish itself, image processing, which uses artificial intelligence to determine how fresh the fish is using attributes such as skin and eyes of the fish, an electronic nose, which is used to assess the odor of the fish, an attribute-based encryption chain, which is a form of security to prevent unauthorized users from accessing the blockchain. All this is used in conjunction to provide real-time data on the fish origin, consumer feedback, quality assessment, tracking, and the freshness of the fish. A general overview of BFACT is that when a fish is caught, it is placed into a fish box that has a near-field communication tag which stores the unique fish ID. This NFC technology allows for the fish box to interact with mobile phones and modules along the way from catch to consumer. The fisherman has an app which allows for the validation of the origin proof, and then there's narrowband Internet of Things devices which are installed into the fish box itself, which allow for tracking the quality of the fish real time and also geolocation tracking, so we can see the fish as it is moving along from the sea to the store. And while the fish is being transported, it will be evaluated by image processing and an electronic nose to determine the freshness and quality of the fish as it makes its way to the consumer. The above qualities are stored on the blockchain, and they can be easily accessed through an application programming interface. The BFAC layer consists of 4 layers, and the first layer is the source of the data sources. Here you can find the fish and the NFC tag. Then the data sources are the Fisher app, the narrowband IoT device, the image processing, the electronic nose. All of these are used to pull data from the fish in the environment, and each of these have attributes which confirm that they are authorized to access the multi-layer blockchain. Thus, it is passed through the first layer, which is the attribute-based encryption chain, and then all of the data gets stored on the Internet of Things chain. The same applies for the data consumer. They can access the multi-layer blockchain via a consumer app, a management platform, or a trading platform. As we saw previously, there's a multi-layer blockchain system which allows for trusted and confidential data sharing. There are 2 blockchains, and the first layer that a user must go through is the attribute-based encryption chain, which serves as a consortium blockchain managed by Sydney Fish Market and partners. This chain allows authorized users to access the Internet of Things chain, where the actual data on the fish itself can be retrieved. There are 3 main roles that have access to the multi-layer blockchain, and the first role is the data source, which they have the ability to publish tracking and quality data to the blockchain via a transaction. The second role is the data consumer, which can read the data from the blockchain. And then the final role is the miner, which run consensus protocols to extend the attribute-based encryption chain. They run certain protocols to preserve the privacy and track updates of attributes of any entities on the chain. This multi-layer blockchain uses 3 different kinds of protocols to exchange data between the IoT chain and the ABE chain. All the roles can act as clients and run protocols. The encrypting and publishing message protocol is mainly carried out by the data source and can upload data on the fish to the blockchain. The retrieving and decryption protocol is carried out by the data consumer and is used to obtain trusted information on the fish provided by the data source. And finally, the attribute updates protocol can be authorized either by the data consumer or the data source, and it is used to provide updates on the fish throughout the journey from caught to sold, and all the protocols are facilitated through the miner role. In this slide we can observe the 3 different protocols used and their algorithms. The final section of the paper consists of the implementation and the analysis. The team conducted trials with the snapper supply chain. They collaborated with a fisher that was 308 kilometers away from Sydney Fish Market, and they caught fish about 10 kilometers off the shore. These fish were caught with normal fishing rods and chilled in an ice slurry box, and then the fisher took a photo of the fish using the Fisher app, and then they linked that photo with the NFC tag that was on the fish box. On the right we can see an image of what it looks like in the app, the device, the time and the location of where the fish was caught and when. And this then gets updated to the blockchain. The blockchain has a delay of 5 seconds, so it isn't real time, but that is sufficient, and the blockchain system can handle up to 2.5 million boxes of fish at any given time. Tracking is updated about every hour. Real-time tracking and monitoring was carried out by the narrowband IoT module and a few sensors like the environmental sensor and the GPS sensor. The narrowband IoT module would periodically wake up and obtain data from the sensors and update the blockchain with the protocol hourly. The module would work up to 12 kilometers offshore since it is cellular network dependent, and we can see an image of how small the module is compared to a coin, and we can see some of the data that's being transferred onto the blockchain, like the temperature of the fish over a period of time, and also the GPS tracking of the route of the fish from where it was caught in the sea to the path it's taken on the actual mainland. The battery life lasts about 21 days for this system, and The team was able to send 457 records over a single charge to the blockchain. Depending on the desired battery life and sampling rate, the sleeping time can be adjusted to optimize the battery life. The quality measurement system consists of the eNodes and the image processing, and since these are such complicated systems, they couldn't be easily integrated into the Fishbox, so the team had to use a lab in order to conduct the quality measurements. There is a chessboard method and a rectangular mark method, and they both essentially are used to determine the size of the fish. Then for the eNodes, this device captures the water molecules and converts it to an electrical signal, and then this is tested against a manual indices. The training and testing models used to benchmark the dataset were built up using rich quality annotations provided by Sydney Fish Market quality assurance experts. In the second half of the paper, we covered the blockchain-enabled fish provenance and quality tracking system. We covered the attribute-based encryption protocols, and we covered the analysis and implementation of the overall system.
Some of the key aspects of the blockchain-enabled fish provenance and quality tracking system previously discussed were the implementation of the hardware used for obtaining data, the IoT devices for sending data, the multi-layer blockchain, which consisted of the IoT chain for storing and retrieving data, as well as the ABE blockchain for managing keys and access control. And finally, the artificial intelligence implementation, which consisted of image processing in order to perform fish freshness identification. The hardware implementation consisted on the integration and development of multiple modules and systems. The authors of this paper developed the eNodes module, which was used to measure the freshness of the product based on its odor. The fish boxes with the capability of tracking data such as temperature, location, time, and the capability to connect to a cellular-based IoT server. Also, it contained a power module for tracking power consumption and providing a 3.3 volts with 2200 milliamps battery for powering the entire system. However, the results for this investigation included that the battery life for the system was about 21 days with 1 hour time sleep configuration and 7 days for 20-minute time sleep configuration. This is important to note since during these periods of time there is some data that is not being measured and could compromise the actual measurements for identifying the state of the product, including some type of changing the module or perhaps using different sizes of batteries depending on the estimated time of arrival for the product would increment the frequency for sending data and thus increasing the reliability of the entire system. The IoT implementation, which consisted on the capability of using the NB IoT device, which was able to connect to an IoT server using cellular networks, and then transmitting this information into the blockchain by signing the transaction with the private key embedded within the NB IoT device. During this implementation, the authors utilized the Ethereum blockchain network, which has its own consensus algorithm as well as validators for its own network. This network was used as the ledger to store the data being sent by the IoT device. However, it is known that the validation process for each of the transactions has a delay and as well as a fee, which were not discussed. This is an important aspect since this would affect the delay in which the data consumers receive and extract information. During the implementation of the multi-layer blockchain network, it was implemented a ABE chain that allowed the system to manage the authentication keys in order to send and read information sent by the IoT devices. Then the IoT chain allowed the system to store the information the IoT devices were sending. The IoT chain during this implementation was a blockchain network, and the ABE chain stored the corresponding information in order to access and decrypt the information contained within the blockchain network. In general, the authors of the paper explain in detail the security of the multi-layer blockchain. However, it was noticed that the security of the device containing the private keys as well as attributes in order to send information to the blockchain network were not discussed. The importance securing the IoT device is to protect the access to the overall network. The authors of this paper also utilized artificial intelligence in order to analyze the freshness levels of the fish. In order to achieve this, it was developed a freshness regression algorithm which calculated the overall freshness of the fish. During this case, the freshness was divided into three possible outcomes, where 0 means fresh and 2 means fresh but still eatable. However, the worst case scenario, such as not eatable, was not considered. This scenario is important due to the fact that eating or purchasing a not eatable product classified as still eatable should not occur and damages the credibility of the overall system. The overall paper was very well structured and contained enough graphs, illustrations, and data that helped understand the overall investigation. Also, they explained in detail every component and details of the investigation as well as the development process. However, this paper did not include enough background information and definition of key terms in order to understand the material better. This research is very complex due to the fact that it integrates different types of technologies such as IoT, blockchain, embedded systems, artificial intelligence, and among others. This makes it difficult to understand the overall investigation if not enough key terms and background information is added.
In conclusion, the study provides implementation for blockchain-enabled fish provenance and quality tracking system consisting of multi-layer blockchain architecture and attribute-based encryption. Technologies used in this project include narrowband IoT, image processing, and biosensing. The goal of this project was to provide more information regarding fish origin proof, supply chain tracking, and give more objective fish quality assessment. Major challenge in the industry is transparency, what leads to lack of growth and no innovation. This results in an increased need for information regarding origin, quality, and the temperature of fish. The study provides a great solution with a blockchain that uses artificial intelligence and Internet of Things to provide means to detect fish quality and provide real-time data supplied to blockchain. Thanks to attribute-based encryption, security is no longer an issue in blockchain. Technologies needed to develop the project include mobile application, NB-IoT, electronic nose, and image processing. Now I will talk about a few advantages of this study. So first, it addresses a very significant topic because seafood is one of the most valuable food-based primary industry. It provides a way to regulate fish industry. It also gives information such as fish origin, quality, and temperature for multiple parties in the industry, including regulatory bodies, buyers, and consumers. Finally, consumers can easily navigate mislabeled produce with this technology. Another advantage is that this study properly indicates flaws in other projects in the industry with blockchain. The flaws such as supplying only static seafood pictures and information, as well as lack of real-time traceability. This study provides a simple blockchain solution which is ABE technology, which simplifies complicated key management procedures and provides well-implemented access control. This study is also proven to work in the real-world scenario. It was tested in Sydney fish market by integrating blockchain, ABE, IoT, and AI technologies. Sydney fish market regulatory bodies could store, manage, share, and audit captured data in the blockchain system. The main system is very well explained. As you can see in this picture, authors provided multiple components such as NB IoT device, image processing technology, electronic nose, ABE chain, as well as IoT chain. Another advantage was that the study was well implemented. As you can see on the picture below, we can see the information regarding the path of the fish being transported from one place to another. Finally, every technology used in this study was very well explained. Be fact system design, ABE chain, IoT chain, as well as NB IoT devices were all well described and presented to the user. The disadvantage of this study is, however, that the user has to know IoT system design and multi-layer blockchain very well in order to implement this project, because as you can see on the pictures below, the implementation can be quite complex and difficult. Another disadvantage is the section where the authors talk about algorithms, because for a person who does not work with algorithms daily, it might be difficult to understand the algorithm development and implementation process in this study. This is our source, and these are the references for images that we used in our presentation. Thank you for your time, and I hope you enjoyed the presentation.